Okay, so I hope that now everything runs more or less okay. So welcome to the uh, last one week of this semester. We are slowly approaching the end of this course, which also implies actually as the last year, I may introduce a number of works by one, which is 1 week behind the schedule. Next year it will certainly be better. So now some organization alignment first, and then I will just move to also align what you heard previous week that what I'd like to show today. Yeah, so according to this new rules, which were set up by Vice Dean of Research, Professor Peshkova, I was supposed to announce the final exams today, if I'm not mistaken, which I did in the ecosystem, but these are fake, fake exams in the sense that I just did it not to be sorry, criticized for ignoring this very sensible organization trick, at least I believe. So I think it's really reasonable, except for your case. So what I decided to do is to send you the calls for the 3 weeks of the beginning of the examination period. Please indicate what, you have some plan perhaps in which week you would like to take this course, pick the selected week and fill out your availability so that I can distribute it somehow reasonably. Because unless something has changed, they have not been offered a week. I heard that especially in this English program, people love to concentrate on exams in 1 week, which at some universities is standard, but certainly not here. So if you already know, in the other courses you are taking, what are the final exams, this added flexibility should be just a possibility for you to pick the date which is more convenient for you. Of course, I'm very much aware that none of these options might work for you. Then just wait until I announce those officially in cost again, which will be this Friday, and you can solve it on your individual basis. So any questions, remarks? Have you all received these calls? Yeah, they are French-based and worked for me last time. I'm completely ignorant in French, but everything worked and then really translated into English. And compared to Google, there is not this bunch of advertisements. So my feeling is that Google now is overloaded with that, and this one is much more easy. But let's see how things work. If you have some difficulties in accessing that, let me know. But again, from my layman perspective, it seems to be really easy to use. So this is one statement. The second statement which I also wrote in the email is that some of you, I don't know whether you are in this room or not, have expressed the interest to take the exam in the last week of semester, which I said that, I'll do that, that's possible, but this was really an overstatement. I'm really sorry I didn't take into account some additional obligations, which I will take very soon, and now I need to introduce myself to the Scientific Council of the University and also Academic Senate of the University. And this is exactly something which is concentrated in the last week of semester. So sorry for that. Again, micro planning, but this is the first time that I'm getting to this more administrative position. So any questions? Is everything over? Okay, so if there are no pressing questions, then I would just like to briefly summarize what Mark did with you last week, which was some introduction into finite element treatment for two-dimensional elasticity. The original plan was that we will basically cover all essential steps, but that was too ambitious in my opinion. So we somehow discussed it very briefly, and I decided that I will just go through that. pick up exactly where the point is started, and I'll try to develop it systematically, at least to the best of my possibilities. And let's see. So basically the plan is to cover everything this lecture, and also prepare you for some examples, solve one, and then dedicate the part of the lecture next week to summarizing the last problem I would like to discuss in this course, which is bending of thin plates. And then there will be some dedicated time also to do a bit of calculations of your own or work on the homework assignments. So let's see how this will work. Okay, so now what Mark was trying to cover, at least based on the handouts he gave me after. Oh, sorry, and I forgot one thing. So if there is someone who is really diligent person and he or she is writing notes on his own, then for this lecture by Mark, I would much appreciate if you send me your scan copy, just to see how we perceive that. And I will just incorporate it into this annotated version. So basically what Mark was trying to show to you is how to get the governing equations of two-dimensional elasticity and treat it using the tricks we have developed in 1D. For 1D elasticity, for instance, for stress elements, and I will spend tons of time on that. And just to make this distinction, basically you proceed in a way that you take this set of governing equations, which very non-standardly, I would say, I'm presenting separately, so we don't have a diagram. And I will now distinguish two types of equations. One are the equations of equilibrium, and the other one is the rest. And this is because this equation of equilibrium are replaced by this principle of virtual work, whereas the rest is left untouched. So this is the first development. Then Marek was trying to explain to you how this virtual work done by external forces looks like. So basically what I prepared as well, and what we also try to explain, is that basically the procedure is always the same, because this is work. You always need to take your quantities of interest and convert them to something which has the units, which is the work, which is force times displacement, or if I have some rotary effects, rotation effects, as I will have for plates, this is moment times rotation. But in this version, force times displacement makes perfect sense. So what I'm basically doing here, as I also try to explain, is that I will just take the distributed load and converted it into resultant force, which is Newton, because, you know, this is the intensity of distributed load. So this guy is given in newtons per cubic meter. I will multiply it by the corresponding volume with this representative section, which is delta x times delta y in the incline dimensions, and multiply by the thickness, which is supposed to be the same everywhere for the sake of simplicity, but this is something which can be then generalized. And I need to multiply it by the displacement, and this is precisely the displacement which is in meters, and hence I will get the force. The only difficulty is that now I'm imagining that my structure deforms, so the displacement is not the true one which the structure experienced, but it's just my virtual experiment to have an if the structure would deform a bit on the top of how it is already before, which is exactly this. And now this argument is relatively straightforward. So this is for the x direction, this is for the y direction, and finally I need to sum the contribution of these elementary volumes of these elementary pieces together, which gives rise to integration. So this is what Mark was showing, or I as well was showing you on this slide. And then he also showed you how this can be reformulated using this matrix notation, because this is something which I have already denoted as delta U as a function of X transposed in that previous lecture. And in here, I have also this X over bar under bar as a function of X. And, now one will see the same argument repeated over and over again, because now we are talking about the forces which are associated with the boundary. I will just do exactly the same recipe. The only problem is that these forces in here are no longer volume forces, but these are surface forces or in the jargon of elasticity. These are so-called tractions, and their intensity is given by Newton per square meter, and it's this highlighted square meter. So this is the part of the boundary. Okay? So this is how these quantities differ. Previously, these were body forces, hence associated with the volume. Now these are surface forces, hence their intensity is associated with surface. And that's pretty much the end of the story, because what now I will do is that I will again take these tractions, which are assumed to be constantly distributed per this outer surface, because I'm assuming that this delta y is very, very small. And I will just take the force in here. I will multiply it by the corresponding surface on which it acts. So this is something I can denote as delta fx, for instance, just to make sure that this gets converted to the force, and I multiply by corresponding displacement. And I will do it in the horizontal and in the vertical sense. So here again, I can imagine that I have the same elementary resultant, which actually makes some virtual work on the virtual vertical displacements of the boundary. As I was reminded by Mark, and actually I also realized it when I was traveling the meeting which I had Wednesday afternoon, that there is some slight inconsistency or incongruence in notation, which is somehow related to the fact that this is the argument which holds for this very specific position of the boundary. So this is something which is not generic, but this is specific for the boundary which is vertical. Where I actually the surface area measure by y-coordinate, the differences of the y-coordinate. If I were in the situation in which the boundary is vertical, then this delta x should be delta y should be delta x. And what I mean is that I'm at boundary, so this is what I'm trying to show here, meaning that this gray part is the interior. Yeah, so this can be fixed, but didn't occur. So this is something I will leave for the next iteration. But this is just technicality. What is important is that again, this is the standard textbook formula from a high school, presumably earlier, which says that the work is force times displacement in which it travels with the sign, appropriate one. And this is just exactly the same thing, except for the fact that because my is continuous, I need to decompose it into some elementary parts in which I will include this one. Okay? And the best demonstration of this actual work that forces. Oh, so this is one typo which might have mentioned. Which is actually characteristic by the fact that if I'm in two-dimensional situation, I have multiple internal forces, which in this particular case correspond actually to the components of stresses, or stress components. This is what I wanted to say. And again, I just need to invoke exactly the same argument as before. So if I am, or similar argument as before, because what I need to do in here, for instance, is to take this sigma x, convert it to the internal force, which means that I need to multiply it by this cross-section, because this is the cross-section on which this stress eventually works. So this is what is denoted here as this thickness, which is this direction, which is this direction multiplied by delta y. So this is the first component. So this is something like normal force in one-dimensional specifically trying to explain as much detail as possible. And actually this delta epsilon x times delta x, this is something which is corresponding to some change of displacement, roughly. Meaning, so this is just this one-dimensional argument repeated there. So this is just the application of the claim that in 1D, I have that my virtual work done by internal forces corresponds to integral over the center line. And I had this virtual strain multiplying the normal force dx. So this is something which holds to what is one-dimensional elasticity. And here I'm actually using this argument for this component of the normal stress, where this is just one-to-one copy, except for the fact that I need to, again, take into account the cross-section on which this works. If I just do it in this perpendicular direction in here, this is what I get. So if you just follow the same argument, it actually turns out that these two things, they change the role. But eventually, because if you are multiplying things together, the order doesn't matter. So this is just the same example. And this one, by analogy, again, it can be discussed, but in slightly more or involved way, eventually goes to the very same expression. So in this particular sense, this normal stress and strain, and shear stress and strain components are energetically related together. So these are work conjugate quantities. And if you would like to be really very specific, this is not the work which I have advertised at the beginning of my summaries, which is force times displacement. This is something which is for density, so this is something which is taken with respect to the elementary volume is associated. So if you just have a look about how these things are expressed eventually,
So this is something which is nicely seen here. So here I have this dx times dy multiplied by t. So again, this is something which has the physical units of work done by meter cubic of my material. So again, if you would have your structure in a state of this constant stress shown here, and you imagine that it will be formed in the indicated way, this is the work which you store in 1 cubic meter of material. So again, I do not know how much transparent that is, but this is the best explanation I think if you are doing. And again, Marek was trying to show you that you can represent it using this compact notation using the symbols from the previous slide. So that was next slide. Then this one, which is now really something which eventually goes in the direction which I promised, because now I have my virtual work statement ready. So what I can do now is to take my structure, let's say this load-bearing wall which I indicated, and what Marek was trying to show to you is that if you just count the numbers of your nodes and elements, what you will find out is that eventually if I just zoom in, (20, 21, 22, 23, 24), because I have 4 rows of nodes and 6 columns, if I'm counting right. So in this part, hopefully, he also wrote down that in this particular case, I have the structure, if I imagine that I compose it into the smaller bits, which are these so-called finite elements, then I will have 24 nodes. When it comes to counting, this is 10, 11, and 12. Degrees of freedom, actually, I know that each node has 2 degrees of freedom in plane. So this is something which has 48 degrees of freedom, out of which these are constrained, because in that scheme which I tried to give to you, this was fixed. So because nodes 1, 2, 3, 4, 5, and 6 are constrained, I do not need to determine the displacements of those. I know that from the very beginning. Of course, there is no free lunch on getting reactions there. The reactions which I identify with some sort of, for instance, to check our foundation, to check whether they can sustain this. Okay? So this is basically it. So again, what this tells me is that if I'm able to treat this constituting element, this rectangle, with the same techniques as before, I can eventually see this as some kind of very generalized truss structure which has 24 nodes. So, and these elements, they just serve somehow to actually determine what is the stiffness of that structure. So that's basically it. So if you just think about that, if we are able to formulate all the matrices in the spirit of displacement method, then this 2D elasticity can be converted to some 2D truss structure. If you would like to motivate it via this, and we know how to solve two-dimensional structures. We can this semester 2 to 3 times and last semester as well. So we know all the tricks of the trade, and again, this is not something which is super difficult. So the question is why this method was not used before, and as you may guess, the answer are these numbers. So although this is very rough discretization into so-called finite elements, it turns out eventually that you have 36 unknowns. So even for this very simple model of your structure, you need to solve a simultaneous system of 36 equations for 36 unknowns. And this is something no human can do. So I do believe that this method was known before because people were very advanced in the pre-computer area. But it eventually resulted in something which was unsolvable. So the thing which changed that was invention of computers. They can solve 36 equations for 36 unknowns by very well-established algorithms, and it costs you nothing. So again, the reason why I'm actually showing you all this is that because we have computers at our disposal. So this is something which is embarrassingly easy for a computer. But it's completely impossible for a human being. So let's see how far this can be pushed with the modern recent development of artificial intelligence. But again, in this field, the invention of computer changed pretty much everything. It changed the focus of the methods from something which was analytical to something which, if you can convert to a system of linear equations, you can eventually use. And again, the tools of the trade and procedures of analysis are exactly the same as for process. Okay, so now, however, what I need to do is to evaluate these individual matrices. So what I need to know if I would like to proceed exactly in the same way as I did for process is get the stiffness matrix and get the rules how to transform distributed loads to nodes in order to assemble the final system equations. And once the system of equations is there, then I know exactly what to do. Of course, there is no free range. The problem is that now I'm working with two-dimensional domains. I need to differentiate with two coordinates. I did my best to explain why this is so. And I also introduced one trick, which is called Gauss integration, because when it comes to computing integrals, I told you last time that this is something I will never ever do analytically again. In all fairness, this can be done analytically at least to a certain extent, but the last part of this place is something for at least 2 years ago, MATLAB was similar to this, were unable to do this. So to circumvent that, I need to be able to transform everything by this normalized interval, which in one-dimensional was just this one. But because I'm working in 2D, then I also need to consider this perpendicular direction. So this is now my generalization of this one-dimensional interval. This is two-dimensional interval. And I just need to be able to do the substitutions of algebra. Well, gentlemen, if you need to discuss something, you are much welcome, but not in this room. Okay, so I just need to do this transformation to this square, which is again the normalized interval of the degree. I was a bit nice to myself because I said that my original domain is rectangle, and then if the original area is rectangle, then this transformation can be done in two coordinates completely independently. So because this is rectangle, if you think about that for a moment, I can actually 2 times repeat this 1D construction. Which basically means that in the real domain, what was x is now y, and in this parametric or reference domain, what was psi is now new variable in check or eta, but you can call it in English. You can see that this is exactly the same, right? So if I just take this formula and replace x by y, I will get the bottom part, and the same on the left-hand side, unless I did some stupid typo, as usual. And I will just, these were just one-dimensional formulas, which I know from this one lecture. So using that, I will actually get this bunch of transformation, which allows me to compute everything in the real domain or in the physical domain or in my real structure. Okay, so this was the first thing which Mark introduced to you. And now the thing which he's participating quest is different than I envisioned, but what I try to explain here is that I can develop this idea even further on this reference interval, because I will just assume that per each edge of my element, for instance, I have the standard one-dimensional basis functions. So this is something which is 1D. This is something which is rotated 1D, which means that x is replaced by y, psi is replaced by eta, or any other symbol you wish. And again, because I have this square, which is always the case, by the way, the reference domain, sorry, in anything, then I can actually compute these basis functions as products of the one-dimensional. So this is what I wanted to show here. So this is again a recap of one-dimensional element development. This is exactly what I did in 1D. The only difference is that I'm saying that now this is arbitrary coordinate. Which eventually means that this can be either psi or eta, so this two reference coordinates. And if I do product of these two functions where this symbol stands for that one, and the product with those functions where this symbol corresponds to eta, I'm getting 4 basis functions in total, and they are always of the form that I have this 1/4, 1 plus minus psi, 1 plus minus eta. And depending on which function it is, this plus goes to minus. This is how they look like. And again, the argument is that I do everything in those two directions independently, and then I do combination of these two dimensional arguments. This normalization factor 1/4 is just to ensure that the basis functions actually again attain this value of 1, as shown on this picture, which is still not perfect, but much better than everything that I presented so far. But I never know how to rotate it in a way that is visible in all cases. And this actually comes from the fact that because Gauss quadrature is usually defined on this interval of dimensional strength 2, then I just need to normalize. Because we are basically doing this on 2 by 2 squared. But this is just technicality. So that's it. And now comes, depending, whether you see it for the first time or whether you have seen something like it before, which you did, but I don't know whether this is visible at the moment. So what I'm now trying to do is to recall this principle of virtual work statement. And write this, but write this only at the level of my element omega e. And I know that if I will go through the procedure, then actually from the term on the left-hand side, I will get my stiffness matrix. Whereas, for the term on the right-hand side, I will get some vectors of equivalent forces. So this is what I did in 1b, exactly, but here the difference is that I have two types of distributed forces, ones which are distributed over the surface or the boundary, and the second one which are present in the body, like gravitational force, for instance. So this is something I need to distinguish and make actually two separate recipes. How to take this distributed load and convert it to equivalent normal forces. And the trick how to do this is relatively straightforward. So in each node of my structure, as I actually had in the truss after I did it in one-dimensional domain and then did boundary Fourier transformation. But here I have really two independent degrees of freedom which characterize this virtual displacement. So what I'm now trying to do is to express this virtual work done by internal and external forces. If I take one element within my structure and I prescribe this virtual displacements to its nodes. Okay? What is different though with respect to cross structure is that there is this great area which is in between or among the nodes. So I need to be able to take this information and from that somehow consistently so-called extrapolate it to the interior of my domain. And this is exactly what is done here. This is exactly what is done here. And if you just see how things are done, what I will do is that again I will combine the data for each node separately. You know, so you can see that the changes in this scheme the other stuff just remains the same for the whole. And I did that already for process, so this is something that we do here as well. There is no difference of changes. The problem is, however, that now I have two independent components within my structure. If I now realize that this is actually a column which is 8 rows and whereas displacement has two independent components, it turns out that just to have this sizes matching, this must has 2 rows because of these two independent components and 8 columns because of 8 parameters of my virtual displacement field which is expressed by the nodal quantities. And because these two directions are again independent, then actually it turns out that what I do is that I will put this N1, N2, N3, and N4 in here and pad it by zeros at the remaining places. Because if I do this matrix column multiplication, that actually this horizontal component gets completely unaffected by the vertical ones and vice versa. So this is what I was trying to say, that this perhaps might be something which is a bit non-standard if you see it for the first time, but if you see it repeatedly, then this is standard. And perhaps it can help you to visualize that actually what I'm doing is that I'm doing this interpolation again node-wise. So this is the block which is corresponding to 1, 2, 3, and 4, and I'm doing it in the same way. Although I do not know whether this really helps. So in terms of some compressed notation, this is the virtual work done by, this is the parameters of the virtual displacement, so these three numbers. And this is something which is denoted as matrix of basis or shape functions, as Mark told you, and has this particle dimensions. So now what I say is that my virtual displacement as a function of x and y is approximated by my matrix of basis function, which depend on x and y, multiplying delta dE, where I would like to highlight again that these are data and the vertices of my element, so this is constant. So this is something which is in R, this is something which is a column which is 8 acres. So this is constant. And this is important because one dimension we're trying to get are something variables, because as I tried to explain to you earlier, the structural work statements are done by taking your structure, decomposing it into elementary parts, then using some very elementary this gives rise to integration. So if something is constant, this is something which is actually unaffected by integration, or very easy to integrate, so this is something which is quite good. Also, some people explain this finite element method as really not taking these elementary bits, but taking the methods, the elements of finite size. In my opinion, this terminology, which is natural, check because it was improperly, it was not properly translated. Actually, in English, it's. But anyway, sorry, I'm talking about things I shouldn't be. So now, here is basically the argument. So now if I look at my element and try to compute what is the work done by external forces, but by forces in particular, I know from the previous one that this is given by this expression, but now I'm just integrating things only over my element, so not over some arbitrary body, but my very specific element. And if I do this transformation to the coordinate system in the dimensionless coordinates, this is actually something which is completely element independent. So the mental picture then is that I have these multiple elements within my structure, and they're all mapped to one finite element 2 by 2. And this is what I believe is the proper interpretation of the finite element method. So this is the finite element, and then by this substitution formulas and then coordinate transformation or coordinate transformation formulas, just specializing for particular elements in your basic. So now what I will do is that on the previous slide I have justified that instead of virtual displacement, I can actually plot I can substitute the virtual displacement by this expression where I forgot this E superscript. And then I just use the rule which says that if I have program with two matrices and transpose them, that actually everything gets transposed. So I know that. If I just do the substitution, then this needs to be transposed, meaning that I will get this term, that term, this term, that term. This thickness is just taken out of the argument because this is constant in the same way as the displacement. And if I do that in this way, that actually I have expressed my work done by external forces within this approximation as a matrix multiplication of this delta dE, which are virtual which is the virtual displacement, at nodes, times some matrix. And this matrix, as I know from the 1D case, is my matrix of 1D, my matrix of equivalent number forces. So this is the definition. This is how it is derived. But now I start to be a bit more cautious because it contains some integral, and that integral, and I promised myself that I will never do by particle integration, so I would like to use Gauss quadrature instead of that. But for that reason, I need to transform it to this reference domain, so to this omega over hand. So what I will eventually get is that because of the substitution formula, actually this gives rise to Lx times Ly over 4, where this E and T is the volume of my element, so this V is my volume. And this is the remaining part, which is now to be integrated, but it's now transformed to this minus 1, 1 integral twice, so now I can employ the Gauss quadrature. And just an illustration how this works, if I assume, for instance, that its intensity of body loads is constant everywhere, then I can just run some analysis, which is documented here, to find out that actually if this is constant, so this depends on the zeroth polynomial of psi and eta, this is at most of the first term. So if you recall still how this Gauss formula worked, if I'm supposed to be not like here actually I need to do it twice. So I need to integrate with respect to both coordinates. But because there is no summation, actually, I'm just evaluating it in one point, I can eventually say that the only thing which I need to do is to take this quantity and substitute it in there. I just need to be a bit more careful because I also have these integration weights in there. These are equal to 2 and 2, and hence this 4 vanishes. And now if you just substitute these basis functions and do the matrix multiplication, this is what you get as a result, which is in hindsight not really shocking, because if you have your structure, you look at one finite element of it, and you have here the x over bar e and y over bar e, so the distributed load throughout the whole volume, and it is also of certain thickness. Then you will take just the horizontal resultant force Fx of element E, which is the intensity, times volume, and that volume in particular is thickness times area of my element. And I distribute it equally to all nodes. So I will say that 1/4 of this Fx goes here, 1/4 of this Fxe goes there. Here I get 1/4 Fxe distributed here, and here I have the 4th of the result. So if you recall how we transform these distributed loads in N forces or equivalent forces, they just differ in sign. This is pretty much aligned with the argument. Again, there's nothing mysterious with that formula here. And this is what which I will ask you to corresponds to forces. So resultant we distribute it one and distribute it. And of course, the same argument is repeated in perpendicular direction. Now there is this argument of the virtual work done by external forces, which was not really prepared well from my side, but again, actually after preparing these handouts, perhaps I realized that the most straightforward argument, which is just demonstrated by this computation, is that I know that if I'm locating the edges of my structure, then I'm actually exactly recovering this 1D basis functions. I can just employ the 1D formula. And if you recall, this 1D formula were just the data stored in these tables of N forces just with the minus sign, because these are N forces, these are equivalent nodal forces, so they appear on the right-hand side. So here, for instance, if I said that over this edge, you have some load of constant intensity, which has two potential directions, horizontal and vertical one. So you, again, if you just have a look, you will take the by the edge length, which is here, take the resultant, which is 1/2 here, and distribute it 1/2, 1/2. If you have this triangular distribution, you take this one-third distribution, and if you have something here, you can just decompose it into constant and linear part, as we did in the last semester. So this hand calculations for calculating the nodal forces is something you can do. So this is something which I know from structural mechanics 3 already. I just need to be careful about which sign I use. Okay? And this is, at least from what Mark explained to me, the part in which he finished his presentation. So it took me 1 hour to go over that. For the completely realistic and estimating how far it can go. Okay, so now I will proceed exactly at the point at which Mark stopped, which is here. And I'll just try to convince you that we can learn a lot of stuff. So again, what I'm required to do now is, because if I just do the check, so I have this W and Wx of my if element, which I actually expressed as a matrix multiplication. So I have this delta dE, which are these virtual displacements of my element, and I have already identified that I have two N forces associated with nodes. One are because of distributed flows, which are computed in a very natural way, and then I have the contributions which come from edges of my element, so for this gamma which I can view, I can explicitly evaluate using this one-dimensional and force table. So this is what I already know, and I have it. So the final bit which we make internal work done by internal forces. Sorry. I already know these are the virtual displacements of my nodes. DE are the true displacements, not the virtual one, the ones for which I search by solving the equations. And K is the stiffness matrix of my node. And again, if I do so, then the method is completely ignorant about, what is the physical problem from which these numbers came from. I can just use exactly the same procedures how to manipulate them. So hopefully I will at least hope that. So again, this is something which I would like to do. This is something I have done, so I have my equivalent of this force calculations from structural mechanics 3. Again, just very natural or reusing what I already have. So now, if you just have a look at the previous line of argument, then Mark did his best previously to actually see or say that what I need to do is to take this virtual strengths within my element and multiply them with stresses in a way that I will just actually match the corresponding stress strain principle. So as it goes from the part, this part, I know exactly what I am allowed to do. So I know from the previous developments that actually this bit can be replaced by taking that matrix of basis functions of my ETH element as a function of x and y, multiplying the virtual displacements of my element. Okay. So this is the substitution which I know already from the arguments. So now it turns out that here I have some new guy appearing in the formula, which is this matrix of partial derivatives. If you recall, it is precisely this partials. It is something called symmetric gradient or symmetrized gradient matrix, or I can call it in the way you wish. So now this is something which precedes this matrix of basis. And I would know where I made very explicit, but especially in this course, I'm trying to be very careful in saying what is always constant and what can potentially depend on x, because it decides a lot. So just to highlight this, I would like to say that actually these partial derivatives are taken with respect to x and y coordinate, which is here represented by this x. So this is also this operator. Okay. So now this term is actually something which contains x dependent, so I need to apply this to the matrix of basis functions first. And if I do it, I get something which I have already discussed in one-dimensional elasticity, which is this so-called B matrix, or some people also call it symmetric gradient matrix, even if this corresponds to finite element analysis. And again, this is nothing else than taking the partials with respect to x and y, as indicated there, and applying it to the matrix of basis functions. But, this is something which I know already. This is something which I know from the current lecture, which is 9. Whereas this is something which I know from the previous lecture. So this is something which I know from lecture 8. Okay, so you just look back, you will find the examples. So I can, in principle, do the evaluation. The only problem is that I know that I also will need to take care about the integral of my finite element, but this is something I will do on this reference domain, on the square tutu, which is no matter what my original element looks like. So for that reason, actually, I would like to do this slightly differently, meaning that I would like to transform this x dependence to the dependence on this parametric coordinates, okay? As they are written here. And in order to do so, I need to acknowledge the fact that actually I have never explicitly written by these how these basis functions look like. So this is what is presented here. So these were these plus, minus, and 1 over 4, if you recall. I also made it very explicit that actually these are completely independent of the element, because there is no e in the superscript, so this is something which is implicit at it. But now, I'm asked to perform this derivative with respect to x. What I need to do is actually perform derivatives with respect to y. But actually, because of this 2 times 1 dimensional coordinate transformation, I have these formulas ready. So basically, every time I write here the partial with respect to x, I can equivalently well write here 2 over Lx E partial with respect to psi, my bad. So this is what I can one-to-one replace. And you can see that actually this is present in 2 positions in this operator matrix. So I can also insert it there. And for every partial with respect to y, I actually need to substitute according to this rule 2 over Ly of element E partial with respect to eta. So this is the first entry, and this is the second entry. Okay? So now depending on your aesthetics, but at least to save a bit of writing, I will factor this 2 out of the diagram. And now I will just imagine that I'm doing this differentiation. So now the empty spaces are occupied by 0, and if I'm interested with this in this entry here, then the only thing which I need to do is to do multiplication of this row with that column. So if you just do that, it turns out that I will get 1 over Lx of element E partial and 1 with respect to the corresponding dimensions. If you do the multiplication of this type here, so this would be horizontal, vertical, you will find out that actually the zeros alternate, which means that they just there will be no contribution. And I also know, and now this is gonna be a bit tough, that actually the same guy is sitting in this position here. Because if I just do this multiplication, I will see, sorry, if I will just multiply the third row with the second column, I will see here again the same function. So this is an elementary block which now repeats. So this is something which is actually specific about node 1. And if I now would like to extrapolate this to so sorry for cheating a bit, but now I would like to extrapolate it to the corresponding nodes. So basically the only thing which I need to do is to change this 1 to 2, right? If you just imagine the way or envision the way how the data were collected together, I really made the best effort to separate these nodes from each other, and hence I can imagine that I'm just doing this multiplication to each of these individual slices of the matrix. So now I will just repeat the same argument again. I will just duplicate this, change change 2 to 3, and same here. And now I just need to repeat it for the final fourth node. So this is what I got. Okay. And by that I actually treated all partials with respect to x. Now I will need to do exactly the same thing with the partials which are with respect to y. So now if I imagine that I'm doing this second row first column calculation, I will find out that this is 0. And here I will have eventually 1 over the edge length, but in the y direction. Here I will have my function n1 differentiated with respect to the second dimensionless coordinate, and this is pretty much the argument which is repeated over the remaining entries. And finally, again, if I just imagine what would happen if I were to do the partial derivative with respect to y, so this first row times first column, I will see that eventually here I have exactly the same thing here. So this one. So again, I just need to distribute it accordingly to the remaining places in my development. So this is 4, 3, 2, and 1. So it was a bit lengthy. I'm very much aware of that. My main intention was just to show to you that it's not complicated. It is just tedious. have everything actually done on the nodal basis. So this multiplication, because of this very special structure, actually can be done slide by slide. I will get these expressions and repeat it and thus x. So this is how I should have done it here. And then, if you just have a look here, these basis functions are very easy. So if I do partial derivative with respect to x and y, what I will eventually get are just some constants and individual entries which are linear in one coordinate or another, but never simultaneous. Which is different from how the functions look like for the displacement, because then you have this terms which actually contain product of these two coordinates, x and y, or psi and eta, and hence these are so-called bilinear functions, but these are just linear functions. Okay? So this is something I can do, pre-compute, store in the code, and down. So now I just need to finish the rest of the argument. So I now know exactly what I can substitute in here, because I have treated this B matrix. Yeah, and sorry, and the last comment which I made, wanted to make, but I did not make actually, is that eventually this gives me this B matrix, but now expressed in parametric coordinates. But because these derivatives, when scaled to the reference domain, they actually depend on the physical dimensions of the element. So this B matrix is dependent on the element. Just for normal, just for shape functions for this n, I got something which is completely geometric. Here, in order to be able to determine the derivatives in the physical space, I need to know at least what are my dimensions. And this is what it makes this dependent on, this is what makes it dependent on the elements. So this is the maximum it can reach. Okay, so now, just to finish the argument, I actually need to express or explain how to evaluate these stresses based on all assumptions which I made. So again, if you just have a look at the previous lecture, which was actually 8, I'm sorry, then I really run a lengthy argument in which I also have tons of typos, just to show you that actually the relation between stresses and strains can be written for two-dimensional elasticity in terms of this elastic stiffness matrix. And I will just say that I will assume that this is something which is constant per element. And hence it's x independent. So again, if I localize myself to one element, I will assume that this is something which is constant. Which, by the way, shows me how to treat problems with non-uniform coefficients which are even discontinuous, meaning that you have very immediate change in material properties or equivalent stiffness, which is again something which is very difficult to do if you believe in the standard form of equilibrium equations. Here it just follows tangent. Okay. So now, in order to say how my stresses look like from this generalized Luke's law, and sorry, I also forgot to say that this depends whether I'm the matrix, how it looks like, whether I'm in plane stress or strain. So this was the critical parameter or assumption which told me whether I'm using the same sort of equations, I'm analyzing this very thin piece of material or something which is really elongated in the outer phase. And now I already know how I have treated my displacement. So I said previously tons of times that my virtual displacement of the level of the element is actually expressed in terms of these basis functions multiplying delta dE. So now the only thing which I do is that I'm very much aware of the fact that these strains are not computed from virtual displacements, but the true ones. So the only thing which I need to do is to delete this delta and get the first expression, which is shown here. I also know that when it comes to the real calculation, I actually need to transform everything to the reference element. But here, you know, this is a transformation which is actually independent of elements. So this is this dimensionalization, sorry, the conversion to this dimensionless coordinate. The magnitude of the basis function is also dimensional. So this is how it looks like at the level of the reference element. In order to get this expression in terms of strains, the only thing which I need to do is just to differentiate those with respect to x exactly as I did before. Sorry, here I forgot to add that this is the derivative with respect to x. So this is what I have here, right? However, I know that I need to perform this differentiation in the reference domain, because this is where I eventually will compute my integral. So this is what I know from 1D. So it turns out that now I will do this derivative with respect to this psi coordinate. And again, because of this coordinate transformation, now actually this derivative becomes dependent of the length, on the length or the dimensions of my element. Dimensions of my element. If I just now take this previous expression, sorry, my son is calling. So I'm taking this multiplication or the differentiation to something which has been previously expressed. I'm getting here this B matrix of element E, but in the parametric domain. So instead of x and y, I actually have it dependent on C and eta, and I need to multiply it by the normal displacement, by the normal displacement. And when it comes to stresses, this is now very straightforward because there is no derivative involved. Like in here, I will just do one-to-one transformation. So the only thing how to get from stresses to strains is to pre-multiply the previous relation, this dE by dE in the corresponding point of my reference. So what I literally did is that I took this expression, copied it here, and pre-multiplied by d. But I'm doing that in different basis, obviously. I did it very quickly. And finally, this is what I'm trying to express. So I am trying to compute the work done by internal forces. And I'm already over time. So, sorry? Okay. Good. So now, I will just do the substitution. Now, because I have the product of these two matrices, and I have this transposition exactly because of the same argument as before, I can write this in this manner. And now I will just expand it. I will write it in very specific order because I already know what I would like to do. So I will write this first because I would like to see it first in this expression for the stiffness matrix. Then I will multiply this by this B, E as a function of X transpose multiplied by this DE, which is constant, but there is no way how to get it out of the integral because these are not numbers as for plus, but this is this 3 by 3 matrix of material stiffness. And I have this BE, which potentially depends on X. And here I will write this DE, which is external to the expression. And the reason why I'm doing that is that I will say that I will pre-integrate of my element this piece in order to get my element stiffness matrix. So if you just compare it to 1D elasticity, it was exactly the same story. Here I have cross-section area, here I have matrix B, here I have my Young's modulus, one number, and here again I get 1D, which was just either row or column, whether this was transposed or not. So this is exactly the same formula in principle, except that physics now dictates that all these objects as they appear here are more involved, and also this is something which is 8 by 1. So now I need to, use eventually quadrature. I was using millions of times the argument that, I'm doing that because I will eventually integrate everything on that reference -1 to 1 interval. So this is my omega hat. This is the reference domain which lives in the dimensionless world independently of all physical elements. But I need to do the coordinate transformation, so I do not want to repeat it over and over again, but if you recall this dx and dy, these are half of element length in one direction and another. Then I have this prefactor of t. So if I just do it explicitly, I will have this constant, then this element in the x direction, y direction, multiplied by 4. And if I do that, then I have equality between this dx, the increments of the x coordinate in the physical and reference. So I have some prefactor. As for this distributed load, if you recall, I can easily identify that actually this is the volume of the element scaled by 4. And I know, again, from the previous developments, that if I pick a proper Gauss rule, then this integral can be expressed as the sum with no error, so there is no approximation or something like that. This is exact. This is how this was eventually computed. So this is the final decision which I need to make. If you recall, I said previously that this B is linear in x or in the dimensionless coordinates. So this actually implies that this can be taken as the first order polynomial in the dimensionless coordinates. But then logically this is also first order polynomial in those two coordinates. And again, this is just repetition of the argument, which says that these derivatives, which appear in this B matrix in the physical space, can be substituted with the ones which I'm eventually using. But I must account for this change of size, or Jacobian or Jacobian transformation. And this is just to remind you that if I do this differentiation, I really get this result in place. So it turns out that if I just do product of two linear functions, I'm eventually getting second order polynomial in psi and eta. So I'm integrating in two directions, but in all cases, actually the function contains this psi's and etas in the second power. If you just do the algebra, you will see it. So I need to pick one extra integration point, meaning that I will use now the Gauss rule of the second order. So I will take the integration points on this reference domains that are symmetric with respect to the origin of the interval. There are either plus or minus 1 over square root of 3, which corresponds to roots of one very specific polynomial. And they are associated with weights of 1. So if you just scan lecture 7, this 1D elasticity, this is what you find there. So the only difference now is that actually now this is just repeated in with respect to two independent coordinates. So I need to sum over these points these weights. Fortunately, they do not matter because they are equal to 1. So I can ignore them. So what I will get as a result eventually is that this is the volume of my element divided by 4 and this double sum of B transpose dB. So if I just summarize that in the final slide, I can just organize my points which will occur in this double sum in here. I can organize them into 4 so-called integration points. They are located at somewhat exotic locations. They are just spread LE over square root of 3 apart. This is because of this Gauss quadrature. And it turns out the only thing which I need to do to get my element stiffness matrix exactly is to evaluate these B's in these 4 points, either one by one or separate and then sum the result. And in each Gauss point or integration point, perform this integration. And once I have the sum down, then I need to multiply by the Boltzmann scale. So this is not a closed form expression as it was in one-dimensional elements, but in terms of implementation, this is code of that one, including the integration table. And this pretty much closes the story because again I have this tabular computations to get my node of forces, and I have this formula which I cannot evaluate explicitly because it's too long. But I can actually represent it by a function in here, which just takes as an input this D matrix, the geometry of my element and the thickness in the out-of-plane dimensions, and it will return this quantity to me. It will just do the sum over 4 indices and cause this D matrix. So this is one extra thing which appears in the in that updated code base. Then also, just to save some writing for you and also for me, I prepared or uploaded a new function which is called elasticity matrix plane, which gives you this matrix whether you are in plane stress or plane strain. And final one is that you will take the displacements to that function, and it will provide you with the stress state at the center of the element, just by actually running the formulas which I have before. And this gives you enough tools to compute two-dimensional problems which are composed of rectangular elements. Then also there is some new stuff presented in the code base, or this is something which was presented by I have never I did not comment on that. So this is something which is related to some helper functions. The first helper function, just for a given node, gives you the numbers of that using this simple transformation. And the second one does this solution of the partition system, meaning solving for unknown first, and then using them to get the unknown reactions. So this is something which we have been doing manually, so now it's time to do it. Okay, so again, I was maybe behind the original plan, but this is something I wish transferred to the problem session on Wednesday, so we will just go over this simple example and show how this is implemented in MATLAB. But trust me, if you just have a look at it, you know, this is something which is, there's no difference almost between doing two-dimensional elasticity calculations and trust for frames. So I will just show you how the logic works. There are also these helper functions to make our life easier, and we will just go over this code, and then I will also show you how the final work of this course looks like, and yeah, and we will also hopefully start some introduction to plates and their finite element treatment. Okay, so thank you very much for your kind attention. I'm afraid it's now exactly documented how much time I took extra from your life, so apologies for that, and see you.